Hi, my name is Josh Engels. I'm an undergrad at Rice University studying math and computer science. This is a pre-recorded presentation for the 2020 International Conference on Cognitive Modeling. Let me start by introducing the topic of my presentation, bad ballot design and how to fix it. Remember the butterfly ballot in 2000? Bad ballots decide elections. Ideally, we could do usability studies for every ballot before they ever reach voters, but there are thousands of counties in the US, so that's basically impossible. Enter ACT-R, a tool for modeling human behavior. We thought, if we can't run every ballot through usability study, why not map the space of human voting behavior, build models for every behavior observed, and then wrap that all in a single tool to bring usability studies to everyone. This presentation focuses on the modeling section of this tool, and describes how we designed a system for simulating and analyzing a wide variety of voting strategies. There are two main parts of our ACT-R system, the ballots and the models. For now, the ballots we pass into our system are generated by a computer. We can customize the generation by varying spacing parameters and the number of candidates for each race. The models are the really interesting part. Each ACT-R voting model is actually composed of 4 ACT-R submodels that can be mixed and matched at runtime. These submodels are macro navigation, movement between races, micro navigation, movement within races, encoding, figuring out what each group of text within a race is, and selection, actually choosing and clicking on a candidate's bubble. This modularity gives us the power to simulate thousands of different combinations of voting strategies from just a few sub-strategies. We first built the obvious sub-strategies to make sure everything worked, but that didn't lead to many voting errors. So we decided to build an alternative macro navigation strategy. Instead of going top to bottom and left to right, it went left to right first and then top to bottom. A run of the model on a simulated ballot is shown here, where the green path shows the way the model voted on the first few races. Note that one race, the Commissioner of Agriculture, is skipped. The model misses it as it goes back and forth. We didn't plan for this to happen. Behavior was emergent. Now that we had a strategy that seemed to make organic errors, we decided to dive in and analyze the errors in more detail. Could we actually spot bad ballot design? We ran the left to right and top to bottom model on 6,600 randomly generated ballots, with all combinations of ballot spacing variables, and analyzed the resulting error data. First, we should note that the average error rate across all ballots was 13%. While that's higher than experimental rates in human voters, it's to be expected, since the strategy we're testing is non-standard. The error rate is the percent of races the model means to vote on but misses. This first graph shows the model's error rate by column. The model is more likely to make errors as it moves away from the left column and towards the right, which also makes sense, since that's where races can be most vertically displaced from the leftmost races the model uses to anchor its position for each horizontal voting line. This next graph goes one step further by creating a heat map of model error on the ballot. The bottom right corner has a spike in error rates, which is because races crammed into the corner are frequently missed if the last left to right voting line is above them. However, other than that, the errors are pretty much uniformly spread throughout the ballot, which is actually a good thing. It means that most errors are ballot specific, and after all, our system is built to find ballot specific errors. So now let's launch some ballot specific data. This graph shows the error rate by the amount of vertical space between races. Basically, as the races get crowded closer together, the model is more likely to miss races. This is good. Race crowding is definitely a bad ballot characteristic, and our model successfully found it organically. Here, we see the rate the model misses races plotted against the distance to the closest race in the column before. This is basically a measure of how horizontally lined up the races are. As the distance gets larger, the percent error goes up. This generates some clean advice to ballot makers. Try to line up your race headers horizontally. Finally, our last graph shows the model's error rate by the size of the race. The model is a lot less likely to miss big races with lots of candidates, and a lot more likely to miss small races with fewer candidates. Maybe our tool could eventually point out these races and suggest to the ballot maker where to move them so that they won't get missed. To summarize, we had emergent model behavior that caught real ballot design problems. We didn't program anything in, we just made the models. Furthermore, the modularity of our system worked, paving the way for us to build many more strategies that catch many more ballot errors. Finally, the dynamic ballot construction showed that our models could run on many different ballots. So eventually, we'll be able to feed real-world ballots to our models. There are many directions we plan to take this project in. We need to conduct eye-tracking experiments to completely explore the voting strategy space. We need to dive into the guts of ACT-R and expand its grouping of visual navigation capabilities so that we can better simulate different voting techniques. And finally, we need to actually build lots of new strategies. That being said, we already have something here that is extremely promising and doing something extremely interesting, acting as a human would and making mistakes. Turns out, that's a pretty hard thing to get a computer to do. Thank you.